Okay, I would like to introduce then to the next speaker. Next speaker is Professor Tony Parry. He's Associate Professor in Nottingham Transportation Engineering Centre at the University of Nottingham, where he teaches sustainability construction at undergraduate and master's level. And his research interests include LCA and carbon footprint methodology, as well as sustainability assessment of construction products and transportation infrastructure. Tony, I will make you presenter, so you will be able to share your screen in a minute. There you go. Now you should be able. There we go. Also, yes, I want to say that Tony will tell us or will introduce us in the uncertainty in sustainability assessment, something that is very interesting. And I would like to say that Tony and I spent, when I was in Nottingham, quite a few days with quite a few lunch breaks with Tony trying to teach me how to play bridge. So I really hope that uncertainty in sustainability assessment is easier to understand, because to be honest, I don't think today I still understand it fully. So Tony, thank you for joining, and if you are ready, the floor is yours. Thank you.
Ratio, when we're allowed to travel again, I'll be sure to bring the cards and we can pick up your bridge education. Okay, let me start by introducing my co-authors, Diana and Elizabeth, who you heard from yesterday from TNO, and then Ahmed and Luis at University of Nottingham. So the work I'm going to describe today is part of work package 3 of the CEDR Pavement LCM project, and you can find all the detail about this and more in the deliverable 3.1. Which included case studies of asphalt sustainability assessment, as well as uncertainty analysis of LCA results. And it's this uncertainty analysis of LCA results that I'm going to concentrate on today. So we've heard in other presentations that one of the aims of the Pavement LCM project is to help national road authorities to decide whether or not to use new innovative materials about which they naturally have not very much experience, and that there is a perceived risk in their use. And you can only think about risk by understanding uncertainty, hence the uncertainty analysis work. Well, we kicked this off at the first Pavement LCM workshop back last year, and 3 outputs from that are very important to this work. Firstly, a decision about which asphalt materials to include in case studies. Secondly, the nature of the LCA studies that we were going to undertake. And thirdly, an outline in approach to the interpretation of uncertainty. And I'm just going to go through those 3 things quickly now. So you'll find more detail in the deliverables, but here are the 6 case study asphalt wearing course materials. The first one is designed to be a reference material, and then there are 5 others which are meant to be greener, less environmentally impactful asphalt materials. And you can see there in the second column, we've predicted by reviewing data in some cases and talking to experts in others what their reference service life of those materials will be. Either just a central estimate, or for mixtures 2 and 3, as you can see there, where we had a bit more confidence in predicting the service life, a potential range of service lives. In particular, mixture 4 is one designed specifically to have a very long service life, and that's important. I'll come back to that later. We chose at that workshop 3 indicators for the LCA studies, and to undertake both cradle to gate LCA for a ton of asphalt, but then also cradle to grave with a 40-year life cycle. And we began to think about uncertainty and how to represent and interpret uncertainty in results. And the graph on the right here shows on the x-axis one environmental LCA indicator, for instance, global warming potential. And on the y-axis, the probability that a mixture might have a particular value for global warming potential. And the blue curve is meant to represent a material for which we've got quite a lot of experience and quite a lot of confidence in the quality of the data going into the LCA study, and hence that's quite a narrow distribution. The brown curve then is meant to represent maybe a new material, an innovative material with, we expect, a lower global warming potential on average, but for which we've got less experience, less certainty about the data, and so it's got a very much wider distribution. So all this work is based upon generating what we're calling probability density functions, the shapes of these curves. TNO, they undertook the cradle to gate LCA studies for a ton of asphalt and for those three environmental indicators, global warming, air pollution, eutrophication. And you can see that the results are as we usually see them. They're based upon average environmental impacts for the processes within the production of those asphalt mixtures. So there's no uncertainty analysis. They're cradle to gate, and they haven't taken into account those reference service lives, which, as Braccio said in his presentation, is obviously extremely important. So moving on then to the uncertainty, and we've grouped the uncertainty into two types. Firstly, uncertainty in the data. So this is the inventory data that goes into the LCA calculations for each process involved in the production of those materials. Now, we've been using commercial LCA software, SEMA Pro, which relies on the EcoInvent database. And fortunately, the EcoInvent database comes with a methodology for predicting or defining, trying to understand the level of uncertainty in the inventory data. And it allows you, in fact, to do a pairwise comparison. We've got 6 materials, though, so a lot of effort has gone into reverse engineering that process and writing it into some MATLAB code so that we can manipulate it as we see fit. So the data uncertainty is defined in 2 ways. Those based simply on the measurement, so every measurement is associated with a degree of uncertainty, and the level of uncertainty or the variance of the measurement is defined simply by the type of process. So is it a combustion process? Is it an agricultural process? And then the second type of uncertainty in the data is to do with the data quality. And this is a user-defined assessment of data quality based on those 5 data quality criteria. And depending on how you rank the data quality for those 5 components, this generates an additional variance. You add the 2 together and you've got the variance for each inventory item in your life cycle assessment. Sounds great, but unfortunately in any life cycle assessment, including these, there are hundreds, if not thousands, of processes involved. So the next stage is to reduce the number of processes you're going to consider. And we did that by doing a sensitivity analysis and lumping together as additional rather than individual processes, all processes with an impact on the final results for any of those three indicators of less than 2%. And for example, for the global warming potential of that SMA reference mixture, that leaves 70% of the global warming potential defined by individual processes, and the other 30% all wrapped up into one additional process. And the table on the right shows some of those processes and their indicator values for eutrophication, global warming, and air quality for that reference material. It shows about half of them. I've curtailed the table, firstly so you've got a chance of reading it, and secondly because it shows that right down at the bottom there is the largest value in this example of variability, and this is the coefficient of variation generated by estimating the variance associated with each of these processes, each of these inventory items, by running some Monte Carlo simulations based on the variance defined as described in the previous slide. Much more detail in deliverable 3.1. I haven't got time to go into it all now, but what this shows is that a coefficient of variation up to 120%, that's a large amount of variability. And it's easy to conclude from that that it's difficult to interpret any LCA results without taking uncertainty into account. Now, the second type of uncertainty we've taken account of is associated with those service lives or the durability of the asphalt materials, because over the set 40-year study period, the durability and hence the maintenance requirement of the asphalt defines the amount of asphalt that's required. How did we do that? Well, if you can remember that first table with the list of materials and their reference service lives, where we had a range of service lives for the two SMAs, we took those to represent the 5th and 95th intervals of their durability distribution. Where there was only a central estimate, we took the 5th and 95th intervals to be plus or minus 3 years around that average. Now, if we define normal distributions by those intervals, then we've now got a distribution of durability, and we can do Monte Carlo simulation again to generate probability density functions of the LCA results of the lifetimes of the asphalts. And here you can see the quantities of asphalts associated with those durability distributions for the 6 mixtures. Now then, we've got probability density functions for the durability as well as for the data uncertainty, and we can combine those to give some uncertainty results. And on the left-hand side here, I've chosen global warming potential of the 6 mixtures. So now the central estimates as predicted by the cradle to gate LCA, and the uncertainty associated with each of those based upon the data uncertainty, and then on the right hand side adding the uncertainty associated with the durability for the cradle to grave analyses. And you can see that on the left hand side for each for the cradle to gate 1 ton of asphalt results, you can see that they tend to cluster fairly well. But when you add the durability, then that separates out, and this is reinforces what Brocio was saying earlier about the importance of durability in LCA studies. Elizabeth said exactly the same thing yesterday. In particular, look at that SMA 11 LSL, long service life. The mixture we've predicted to have a very long service life really leaves the cluster of other results. So now we've got not just the central estimates for the LCA results, but distributions of their uncertainty. And that means you can do a statistical analysis to compare the distributions to decide whether or not they're statistically different, to help you in your interpretation of the results. And if we compare these results on the right of the other 5 mixtures compared to the SMA 16 reference material, mixture 1, then you can see that in fact all the distributions are statistically different from that mixture. So it's really separating the mixtures out. So some conclusions. Some of the processes which are important to the LCA results are associated with high levels of uncertainty. So it's very important to include uncertainty in your interpretation of LCA results. By going through that sensitivity analysis, you can identify which processes are associated with most uncertainty. And if they're very important to your final results, they're the processes, or in fact, the phases of the LCA analysis where you should be targeting attention to improve data quality. It's very important to include durability estimates in Asphalt LCA if you're going to interpret the results properly. If you go through the process of assessing uncertainty, you get not just average LCA results, but probabilities, and that's it's much easier to compare probabilities with confidence than it is single numbers. And lastly, although we've only done this for the LCA results, any factor in your sustainability assessment, like noise or costs, for which you can generate a probability density function, can be interpreted in exactly the same way. Thanks.
Thank you very much, Tony. It's been great to see with these very interesting graphs, actually the impact of this durability and the service life on the whole thing. And as I said before, it has a great impact and is at the same time one of the things most complicated to obtain or to estimate. So there's a big problem there. Fortunately, we have the next speaker will talk about the durability assessment and so. But just before, I have a question that we have received. You presented on your slide number 3 some the service life of some mixes. Was this predicted using also rejuvenation steps? That's the question.
No. No, they were predictions of service lives, but well, yeah. For materials where we had performance data from the national road authorities, we used that. And I guess that may have included preventative maintenance, things like crack sealing. But I don't know. We just looked at the time to the first major maintenance event. For the newer materials, the ones we're interested in predicting the results of, where there's very little data on their performance, then they're really just based on expert opinion.
Mm-hmm. Brilliant. Okay, we have another question there that I will send you. I will assign it to you because we are a little behind the schedule. I really encourage you to answer it, and I encourage everybody to send more questions if you have any more questions for Tony about this interesting intervention.
Great. Can I just ask Davide, is deliverable 3.1 publicly available?
First of all, hi Tony.
Hi.
Some people actually asked me the same for D2.1, so thanks for the question. We asked the PEB because the deliverable are for CEDR. We asked the PEB, and eventually we'll provide them available if they give us the okay.
Yeah, okay, because most of what I've talked about, all that I've talked about, is in deliverable 3.1. So yeah, okay.
It would be great to have them available. I agree. Thanks,
It
Tony.
would make our life easier.
Good to see you.
And you.